Yeah, started, well, yeah, started, I guess. Yes, what's the question?
We're getting stuck on 31, and I was wondering if you could give us like
Problem
hints
31?
Yeah.
to get. I got like the characteristic. I tried using that, and then I got it in terms of cosine and sine, but I wasn't sure about getting the 1 minus cosine term in there.
So getting equations 1,
Right,
271,
well,
1, 271.
I just kept getting stuck, so I was
Right,
wondering if there was
so
like a hint that you
what you have to do is you write it as 1 minus I theta dot j, and then that term squared over 2, and then the cubic term, you relate the cubic term to the first two by means of the characteristic equation, right? In other words,
This is 31.
That's the part.
in 31, what you would do is you'd go back to that characteristic equation,
right.
and that allows you to write the cube in terms of the square, the matrix itself, and
Doesn't the square cancel out? So you only have a cubed term and a.
oh, I don't think it. Well, I don't know, but I doubt that it cancels out completely.
The characteristic equation I got as well was a cubed and then just to the power of 1 as well.
Yeah.
So you could divide that out
Oh.
into the cube.
All right, so you're saying the quadratic term cancels.
Yeah.
Yes.
But you can solve for the quadratic term.
How can you solve for it if it's not
Divided
there?
by
Just
Yeah,
multiply
divide
two
by
more
A.
matrices.
Oh, okay, I see what you're saying. Yeah, okay.
Yeah, you just compute you can just compute the quadratic
Uh-huh.
term.
Yeah,
And then the cubic is related to the quadratic plus the linear plus the zero for the term.
yeah, okay.
Well, let's
We'll have
put it
that.
on,
I didn't look at it.
press and hold, or press one,
But I don't know if I
Yeah, there we
got it
go.
all correct.
and so I'm going to do some examples to illustrate the singular value decomposition. And I'm going to skip the last section of chapter 1 in order to start Fourier series.
Correlation
Let's
functions.
focus.
2 questions.
I wanted to. Yeah, I would like to get that
Oh, yeah.
window, the MATLAB window.
Yeah, software.
And there's another one or two that.
Oh, yeah, there
yeah,
you
and the
go.
one after it will
Okay, that's great.
8 vectors.
All right, I think that'll work. And why is it so low? It's supposed to be there?
I think that's something else. That might be something else. I'm not sure how that. Yeah, that's something else.
Okay. Oh, yeah, that is something else. All right, so we get back to that one by going what?
Well, you might want to just mirror. I don't know if you want to mirror the two displays or if you want to.
Well, let's just focus on, we can forget about the other one. This is the important one. Okay, how do we get this one back?
I think yeah, just go there.
Okay. All right, so let me first of all get back to the singular value decomposition and explain it from the beginning, and then do some examples. Oh, also, let me just mention something else that was something that puzzled me as I was lecturing. Remember that we had something like this ANA, and the point was that this turned out to be AN. That's because A has a diagonal form, and A is actually equal to AN summed over N. So consequently, the bra from the left does give you this relation. I was confused about that last time. All right, so the idea with a singular value decomposition is that we have a matrix A that might be m by n. So m rows, n columns, and the idea is that you can write it always in this form where u and v are unitary, and this one is m by m. This one is m by n, and this one is n by n. And I'm going to give examples of all these cases in a few minutes. Now, the idea of what's basically going on is that an A, by the way, let me just emphasize, it's an arbitrary complex matrix. That is to say, it's rectangular, it needn't be square, and it needn't have any special properties at all. And what it does is it maps some n-dimensional vector space into some m-dimensional vector space. So it takes an n vector into an m vector. And what we can do is we can create bases. A basis for this is a sum, say, n comma a, summed over n. And the basis here is a sum m 1 to n, in this case, m equals 1 to m, and I call them m comma b, m comma b. Okay, so we have a basis for this vector space, a basis for that vector space. They're orthonormal bases. And of course, there are infinitely many of them, because if you take any basis and you take your basis vectors and you multiply them by an arbitrary unitary matrix, that takes you to another basis, and that gives you another form. So A labels the basis, M labels the vector in that basis, B here labels the basis, M labels the vector in that basis. Okay. Now, this operator A, of course, can be written as I sub m a I sub n, and when we do that, we get a sum m equals 1 to m sum n equals 1 to n, and we get MBA. That used to be a really popular degree. I guess it still is, but anyway. And then we have NA. Lame joke. So that's what the thing looks like. And so as you shift from, as you vary A from one basis, in other words, as you switch from one basis to another, this changes, the matrix elements change, the vectors change, and so forth. And if you have an arbitrary vector coming in and it hits this bra here, you then get a total salad in the target space VM. In other words, you get a linear combination of vectors, and you know, it's in general a mess. And what you want to do is you want to pick a basis so that you can write this thing this way: a sum on k from 1 to the minimum of m and n. I wrote it as UK, SK, VK. So you want to write it as a sum of dyadics with positive singular values. So these are called the singular values. And these are the left singular vectors, and these are the adjoints of the right singular vectors. and the s's are all non-negative. And of course you might say, well, why are these non-negative? Is there something special about the matrix A? No. It's that you can multiply any of these basis vectors by a phase, and so if this sk was awkwardly negative, you just choose uk to be minus the original uk, and then you flip the sign. So that's not a big deal. Okay. And conventionally, if you do this in MATLAB, as you'll see in a moment, it'll make them all have, it'll start with the big one and then go down to the small one. Okay. Now, when you first hear about this, this theorem, you might say, oh, this is absolute magic. You need some magic incantation, and the incantation is I'll show you the MATLAB incantation, but it's actually a standard result, and let me show you what basically we're trying to do. You see, what happens here is that this tells you that if you let the matrix A operate on the ket, say GL, in other words, one of these guys, you'll get delta KL, SK, and a specific UK here. So it will map the basis vectors VL into the basis vectors UK. And so what we want then is we want to choose a basis in the vector space Vn such that those orthonormal basis vectors get mapped into, each of them gets mapped into a specific orthonormal basis vector of the other space. So it takes VL into UK, which is one of the basis vectors over here, rather than a linear combination of some other basis vectors. Okay. And so I found that when talking about these things, it was useful to have a special notation. So I introduced this notation. So the operator A acting on any old ket, I'm going to write as just AN. And what we want is we want to pick this basis in a special way. And the special way is that these guys should be orthogonal. So we want to pick the basis N such that A maps orthogonal vectors into orthogonal vectors rather than into some mess. And the special vectors N, it turns out, are simply the eigenvectors of this operator, which is both Hermitian and non-negative. A dagger A is something that's intrinsically non-negative. And so, in other words, we're going to choose as our arbitrary basis vectors n such that this is equal to what I'm going to call the eigenvalue En. All right. And now the question is, does A map the n's into vectors that are orthogonal to each other? Well, A on n prime will be A n prime. And if we have this inner product of A n prime with A n, are these guys going to be orthogonal? Well, this, of course, is n prime, A dagger A, because you just take the adjoint of this equation and you get this part. On the other hand, n is an eigenvector of A dagger A, so this is equal to n prime En n, which is, of course, the same thing as En n prime n. But these guys are orthogonal because they're the eigenvectors of the Hermitian operator A dagger A. So they're either automatically orthogonal or you choose them to be orthogonal. And so this is En delta n prime. So this basically is it. That's the choice you make. And once you've made that choice, then you have a basis over here such that when A acts on it, you get each basis vector gets mapped into a vector that's one of a set of orthonormal vectors, or of orthogonal vectors. I haven't shown that they're normalized, but you just normalize them, and then that's okay. So what you do is to normalize them. Let's for the moment assume that the thing is square. It works out. There are these special cases, and when I wrote this section up, these special cases drove me nuts. Well, I shouldn't admit that. I see shocked faces. There's so many details. Okay, so we have these vectors n, and well, the vectors n get mapped into these vectors an prime, and we want these vectors to be orthonormal. And so what we do is we say that, in the square case, we just set the singular value equal to the square root of En. En, of course, is non-negative because it's an eigenvalue of a non-negative operator. And this En, or the square root of En, is the square root of An with An. And so that means that you can define the vectors on the other side. In other words, we're mapping into orthonormal vectors, or we're mapping into orthogonal vectors. Now we want to normalize them. And so the way we normalize them is we say m sub n is equal to 1 over Sn, the vector An, and of course that's just the vector A on n over Sn. And so that makes them orthonormal. So then say n prime mn is 1 over Sn squared n prime A dagger A n, and this then gives us an En delta n prime n over Sn squared, but Sn is the square root of En, so this is just delta n prime. Okay, so we've basically arranged then a singular value decomposition. So the rule then is these vectors here are the adjoints of an orthonormal basis. They're the basis of eigenvectors that are eigenvectors of A dagger A. Then the SNs are the square roots of the eigenvalues of these vectors in this, when acted upon by that operator. And then these U's are just the image that A takes. The U's are the M's, and they're just the image of the special basis, which are the eigenvalues of A dagger A, multiplied by A and then divided by the singular value being the square root of the non-negative eigenvalue. Okay, so that's the essence of it, and some of the confusing details are these. If n, well, first of all, if n equals m, some of the SNs are going to be zero, might be zero for some special matrices. And that's the case when the ENs are zero. So you might have a matrix A such that A dagger A annihilates some of the vectors in the vector space Vn. By the way, the mathematicians call that space of vectors that's annihilated by A, they call it the kernel. And anyway, I lost my train of thought. What was I saying? I was organized to say something. Yeah, well, okay, so you have some of them that are zero. Well, when you have the zero one, if you have several eigenvectors which have eigenvalues, if you only have one that has eigenvalue 0, then that eigenvector is automatically orthogonal to all the others. If you have a bunch of eigenvectors that have eigenvalue 0, then 0 is a degenerate eigenvalue. These eigenvectors are not necessarily orthonormal, but you make them orthonormal. Okay. So that's the case for the square matrix. For the non-square matrix, if V is bigger, if n is bigger than m, then this is a bigger space of higher dimension than this one. So then necessarily A has to annihilate some of these vectors. Because, you know, if you're mapping a three-dimensional space onto a plane, well, you're going to lose one dimension. And so one of the vector that's orthogonal to the plane has to be mapped into 0. Similarly, if you're mapping a small vector space into a big one, well, you don't know what some of these vectors are over here because they're in this big vector space that you don't know anything about. Well, you just pick them to be, you need to pick them to be orthonormal, but there's actually a more clever way of picking them. Namely, you pick them to be eigenvectors not of A dagger A, but of A dagger. Because if you take these guys here, we'll see later, I think, that these guys are eigenvectors of that, and it's sort of obvious. Let me now give you some demos, which I think will make things clearer. So, I don't know how well the screen is going to do with. Oh, what happens? We're in darkness here. This projector needs reassurance or what?
Might turn itself off after like 30 minutes. And it's
And
been
your
about.
computer might be asleep as
All
well.
right, now it's coming
No,
on
I think that
again.
is off.
Oh.
It's in the same circuit as the one.
So we just wait.
There it is.
All right, but I want to get. So again, we just wait for it.
Yes.
Searching. All right, here we are. Okay, so let me show you one. Oh, Jesus Christ. Well, that's the wrong one, damn it. Do I go? Maybe I go over here to. All right, I see that there, but I can't find it here.
Your screen's not mirrored, so you have to put your mouse over and move it into the screen.
You want to come here and do it? Can you figure out where it is? Because I wanted to be able to manipulate this thing.
I think he said that it wasn't. When you have your mouse, you see the cursor?
Yeah.
Can you push it over here? It's on the screen.
Oh,
You have to
good.
Look at the screen while you move the mouse. It's really confusing to stop here. Yeah.
All right, well, let me just show you what I did here. I wrote a little script. If you can interact with MATLAB, of course, interactively, that is to say, in live motion, you know, you put in something and it immediately computes it. But what is sometimes useful is to make something called a script. And the normal MATLAB window has an upper part, which is the script, and then a lower part, which is something else, which is the calculation part. And in fact, can I move this? All right, well, let me just show you what I did here, but I'm now starting to think this is going to be a disaster. I'm entering a 3x3 matrix here, so, and these are just incantations which tell MATLAB not to get confused with anything that it's ever seen before. So you say clear all, flows all, and CLC, I don't even know what that means.
It clears the command line.
Huh?
It clears the command line.
Thank you. And so you say, you define here a 3x3 matrix. Commas separate the entries on row 1, and then a semicolon tells the machine that you're going to do row 2, and then row 3. And then you say USB equals SVD of A, and so that will give us the singular value decomposition. And then I define the matrix AA to be A prime star A. Star is matrix multiplication. A prime is something cute. The mathematicians use prime for transpose, but apparently they also use it for, if the matrix is complex, then the prime means Hermitian adjoint. That is to say, transpose complex conjugate. So then I set E equal to I of AA, namely A dagger A, and then took the square root of E, and what I want to show you is that the square root of the eigenvalues of A dagger A are the singular values of the matrix A, and the way in which, let's just see if I can actually do this. You then hit, I want to hit run, but this is really nuts.
Maybe if you
There.
turn your back.
Okay, change forward. Where the hell is it? It's apparently over there. I don't understand why it's over there. And see, this is not my laptop, and I was doing this on my machine there, and if anybody knows how to manipulate this, do come up to the front and help me, okay? Because this is I want to be able to show you now I've even lost the damn, I don't even know where the cursor is. Yeah, if you can. Yeah, that's a good idea. Okay, good. But and can we get this? Yeah, all right, okay. All right, so now can I move this up and down?
I don't know how to get rid of that. I'm not really a Mac guy. I just know that you can move the window.
All right, well, here, I'm doing it, apparently.
Yeah, there you go.
All right. All right, so there's the top. So at first I defined the matrix A. That's the matrix A. Then the output of this command, that's the unitary matrix A. A is going to be U, S, V dagger. So there's U, there's S, and there's, well, it says V, so I guess that's V, not V dagger. But the expression is U, S, V dagger. So there's AA, that's A dagger A. And then what we see are the square roots of the eigenvalues of A dagger A. And so keep them in mind, 0.37, 1.1, 19 and a half. And now if we go back and look at the singular values, there's 19 and a half, 1.1, 0.37. So you see That's how the thing works. Now, if we go up here, let's see if we can. Okay. So now, that was for matrix A. Now, next I defined a matrix B that was similar. A little different, and I said USB is SVD of B, BB is B dag of B, F is the eigenvalues of B dag of D, and then the square root. And when that runs, then we see. I think the trick is, and you've got to be able, I have to be sort of looking at it this way, I think. Where the hell is the mouse?
It's off to the right of
There it
your
is.
left.
There we go, all right. So let's just come to, there's A. Okay, so here's B, somewhat different. Oh, let's look at A one more. No, I guess that's enough. All right. Here's B. There's U. There are the singular values. I picked in B one that would have a singular value of 0. Notice I chose the second row to be twice the first row. So that means you have determinant 0. One of the eigenvalues is going to be 0. So you see one of the singular values indeed is 0. And then the right singular vectors are these guys. Okay, so B dag of B then is this thing which is non-negative, and the square root of the eigenvalues are 0, 2.2, and 19.1, and they should be the same as the singular values, and indeed 19.1, 2.2, and 0. So that's just an illustration of that. Now the next thing I did was I set C equal to A comma B. A comma B is a clever MATLAB notation that says it takes the 3x3 matrix A, and next to it puts the 3x3 matrix B. So you've got a 3x6. So this is a case where n is greater than m. So C is that matrix. Then we do the singular value decomposition. We set CC equal to C dag of C, and then G is the eigenvalues of CC, and then I take the square root of it. And so if we look at that down there, what do we get? We get, so that's the B. Here's C. You see C is a 3x6 matrix, which you get by doing A comma B. And so then I did USB equal SVD of C, and U now is a 3x3 matrix. The singular values, though, it's a 3x6, and the singular values are sitting here, and then you just have zeros filling out that space. And then if we go up, V is a 6x6 matrix. It's not obvious on this screen, but there it is. That's the 6x6 matrix. Now, C dag of C is a 6x6 matrix. The square roots of its eigenvectors are, well, 3 of them are 0, and then there's 1, 2.4, and 27.3, and those should be the same as these singular values. Yeah, 27.3, 2.4, and 1. The difference is that the convention with singular values is start with the biggest and go smaller. The convention with eigenvectors, with eig, is to start with the smallest and then list the bigger ones, so it's backwards. By the way, let me just mention one of the idiosyncrasies of MATLAB. So we've got G is a 3 vector of the eigenvalues actually it's a 6 vector of the eigenvalues of the 6 by 6 matrix C dagger C. The square, when you take the square root of that 6 vector, you get a 6 vector whose entries are the square roots of the entries of the 6 vector. Well, which it would have to be because it's not a square matrix. If you had a matrix, a square matrix, and you wanted to form the square root function of the matrix, then you write SQRTM of A, or whatever, and then that would do what I said in functions of matrices, namely it would diagonalize the matrix and perform the square roots of the eigenvalues and then multiply and then do the similarity transformation to get back. So in other words, the formula I'm talking about is, so if you do SQRTM of some matrix A, it would be S inverse the square roots of the eigenvectors of A and then S. So it would do that. And what is...
The laptop went to sleep, so.
I mean, you know, like, what did it give us? Like 5 minutes or something, and then it turned off? All right, here we're back again. Okay, so that's that one. Now, this is another case. D is A semicolon B. This takes the matrix B and puts it under the matrix A. Do the singular value decomposition. Do D dagger D. Do the eigenvalues and so forth. And the square root. And so, let's see, that's CC. That's that one. All right, so D then is AB. So this is a 6 by 3 matrix. The singular values are 6 by 6. I mean, the U is a unitary 6 by 6 matrix. S, on the other hand, is 6 by 3, and you see the singular values are up top, and then you have a lot of zeros. And then the matrix V is 3 by 3, and then this is D dagger D, which is only 3 by 3, and it's the square root of its eigenvalues are in fact the same as the singular values. Okay, let's see if there's anything else up here. Okay, well, I defined a matrix K, which is 0, 1, 1, and 1, 0, 0, and if we look at it here, we can see that's the matrix K. And then you remember that we have something called the pseudo inverse, which I actually haven't talked about yet in class. That was going to be something I would. That's the next topic, and so let me just show you the way how it looks. So the pseudo inverse of this. So this is obviously a 2 by 3 matrix, so it doesn't really have an inverse. The pseudo inverse is L, and it's of this one. I'll show you how to compute it. And now if we take K star L, indeed, we get the identity. So L, which is the pseudo inverse, kind of works as an inverse because it gives you exactly the identity. But then if you do it in the opposite order, L star K, which is the next line here, you see you get a 3 by 3 matrix, but it's not the identity. It's kind of like an identity in that it's 1, 0, 0, 0, 0. So those, the first row and the first column are okay, but then the remaining 2 by 2 part doesn't work. It's not the identity. And then if you have a matrix in MATLAB and you want to know what the rank is, you just say rank K, and in this case, it'll tell you the rank is 2. Okay. All right, I think that's enough. So I'm going to turn the lights back on. And yes, I see questions. I have to pay you. Ooh, whoa!
I don't even know that thing,
Oh,
but I have one. I already got one.
oh. All right, but let me do his question first, because I think I saw his hand first. What?
So when we are trying to find the singularity decomposition for A, we looked at AA transpose. Could we also look at A transpose A, like what determines the order? Because it seems like if you have, like, you can have rectangular matrices, right?
Yeah, oh yeah, the whole thing is for rectangular. Now, these are cause of the product, but the kets, dk, are the eigenvectors of A dagger A.
Okay.
And the UKs are the eigenvectors of AA dagger. That'll become clear in a minute when I proceed a little bit. Yes.
Is the nomenclature in the book similar to MATLAB, where if you have, like, there's one of the problems, e to the power of a matrix, does that mean that element-wise you want us to raise each element of the matrix?
So you're talking about one of the exercises in the book?
Yeah, one of the exercises has it, but
Which
also
one?
just 135.
135?
Yep.
Oh, no, I'm using math notation. In other words, natural log of rho means it's this type thing. And so if you were doing it in MATLAB, you'd put an m there if it's square root or exponential. But when it's not square root or exponential, it's actually an absurdly elaborate notation. And I've forgotten, in fact, what it was. I was playing with it this afternoon. But you just Google sign of a matrix in MATLAB, and you'll see there are two ways. One way, if you just do sign of A, you get the element-wise. And then the other thing that you do, I forget what the syntax is, but if you Google it, you'll find out.
I was more looking at the e to the power of something that basically it's, you know, a bunch of constants times one of the
Yeah, well,
matrices.
equation 454, e to the minus h over kt, right? I mean, there I'm talking about you take them, you're exponentiating the matrix. Am I answering the question, or?
I'm confused, and I also don't see an equation of 1.454.
It's in the exercises.
Our numbers might be different. It's
Yeah, our
452
numbers
to us.
must be different. Oh, okay, gotcha. Because I was going to say mine stops at 1.454.
Yeah, all right. The problem is, I inserted an example and forgot that screwed up the numbering. So what I printed out is screwed up. It's probably 452.
You're talking about the row, right? Just the density matrix in the entropy example?
Right.
It's 452.
Yeah, 452, yeah. And so this is something that,
Okay.
that I talked about in,
was not diagonal, you could diagonalize it and then you would.
Okay.
in other words, if you have an arbitrary, I mean, in physics notation, and I think in sober math notation, although I've heard rumors that some of the people on the other side of Lomas like this. They also don't treat the students very well. So I'm very down on my, I'm also down on the administration. Anyway, the idea is if you have some function of A, okay, what you do is you imagine that F is a power series. And so you write this as Cn A to the n. So that's the way in physics departments and in sober math departments, that's what you do. Now, the way in which you can do this efficiently, though, is if you say, let us say that A is a square non-defective matrix, then it will have, let's see, you can diagonalize it as say, S inverse ADS. And so now when you write this is a sum, well, in fact, let me write it explicitly, because it will be easier maybe to see explicitly. So it would be C0 plus C1 S inverse ADS plus C2 S inverse ADS S inverse ADS plus C3 and so forth. SS dagger cancels, and so you get A dagger squared. So then this turns out to be a sum of S inverse Cn A diagonal to the n S, and so this is S inverse sum of Cn A dagger to the n. This thing then is f of, let us say the eigenvalues are A1, A2, and so forth. Okay. So you get, on the diagonal, you get the function of the eigenvalue. So in other words, you could do the whole thing in MATLAB by saying something like I don't know, or even, it's even equivalent, it's even very similar to a singular value decomposition. And then what you do is you just use your ordinary function sine of the in other words, sine of the diagonal is exactly what we're getting here. And then you act on it with S inverse and S, or U and V dagger if you've done the other way of doing it. So that's, in fact, I don't even know why I did this. I could have just written this as U sigma V dagger in the square, in the square case. This is a square matrix. So this is just, in other words, it's U. So in MATLAB language, it's U, F of A is U, F of sigma V dagger. Where I'm using, in other words, for F, you just sine of sigma, and it would do the thing element-wise, but everything's zero except the diagonal, and so that would be the way of doing it. Okay, so let's see. Where are the questions? Yes, you have a question.
Oh, I don't need it.
You don't want candy, no.
I had a question about putting stuff into MATLAB.
Yes.
That I've never done before.
Yeah, well, I'm not a super MATLAB expert. I mean, my advice is you just have a browser window open next to your MATLAB window and just Google your question, how to blah, blah, blah in MATLAB, and something will pop up and answer your question. But if you have a simple question, try me.
Well, I don't think it's very simple, but I wasn't sure how to you give us like an equation, she give us the entries.
You mean how to have MATLAB solve an equation?
No, I know, well, I mean, I can do that myself, but how do you get the entries?
Oh, how do you get an I?
Well, no, how do I get the entries?
Do two nested for loops.
All right, well,
Say that again.
Do a nested for loop. So
I don't
iterate
know what
over
that is.
Okay, so you would do two. So do you know what a regular for loop is?
No.
A for loop iterates through the elements of something. Okay, and it goes through. So it says for element in something. Do this.
Yeah, okay.
Right?
You're saying
do two for loops to iterate over the rows and the columns, and then just make each row and column equal to the expression as a function of I and j.
Yeah. So what you do is this. What you do is Google do loop or do for loop in MATLAB.
Okay.
And this is, by the way, a
Like the number 4.
FOR.
FOR.
So like for this, do this. For that, do R.
Okay.
Right, all of these, let's see, you've got to follow me a little bit with the camera. Just
Well,
completely,
I keep it on where you're going to be drawing your next
all right,
equations.
okay. Whatever, all right, I'm sure you're doing the right thing. Anyway, in most computer languages have something that in Fortran was called a do loop. In C it's called, I think it's a do for or something like it. It's an equivalent structure in C and in MATLAB. And it basically tells the machine for I equals say 1 to do one thing, for I equal 2 do the same thing but setting I equal to 2. And then, let me give you the syntax in Fortran. Sum equals 0. Do I equals 1 comma 10. Sum equals sum plus, and previously you might have defined, well, let us say I squared plus sine of I. And do. Okay. This is the syntax in Fortran. In MATLAB, the syntax is slightly different, but it's the same thing. And what it'll do is it'll sum I squared plus sum I from 1 to 10. So it's equivalent to sum sum I actually equals 1 to 10 I squared plus sum I. And of course, I'm using I as an integer here rather than square root of minus 1. But I in Fortran, I in MATLAB, I think it automatically is, I think MATLAB is able to kind of figure out whether you mean square root of minus 1 or an integer you're summing over. All right, anyway, let me get back to what I was saying. All right, I think we've talked enough about the singular value decomposition because Keith Sanders did something for you about that also, right? In the Tuesday session?
Quite possibly.
There were no SVD examples?
No.
All right, well, I'm glad I did some today. Okay, are there any, so let's have some last minute questions then about the singular value decomposition. Does anybody have any more questions about it? There's an example in the book, of course, where I actually use the I notation. I say x is rand 3 comma 3 plus I rand 3 comma 3. Anytime you say rand 3 comma 3, it makes a 3 by 3 matrix of random numbers. And it understands that I is square root of minus 1.
I do have a question about the singular
Yes.
decomposition.
Yes, what's your question?
Why is this setup geometrically useful? It seems like there is something.
Why is what?
Why is singular value decomposition useful in a geometrical sense? Because it seems like it's doing something geometrically, because you have some diagonal matrices and some unitary matrices.
Well, I mean, all right, thank you. Here, I'm going to give you candy. I mean, I think it's really remarkable that you can take any n by n arbitrary matrix and write it as a sum of positive numbers together with orthonormal vectors on both sides. I mean, that's pretty remarkable. And once you do that, you're essentially done. I mean, what else could you, in fact, in a certain sense, the singular value decomposition is almost all of linear algebra wrapped up into one equation.
But why so?
Why so?
Like,
Doesn't it simplify? Doesn't it like basically just simplify all matrices?
Yeah, it writes all matrices in an incredibly useful form. It tells you that this matrix takes these orthogonal vectors and maps them into those orthonormal vectors with this weight function, with this weighting. So it's just a remarkable formula. And what used to be the case in the education of physicists was that this wasn't covered at all. And I once was at a party in Santa Fe where Cleve Moeller, who invented MATLAB at UNM when he was chairman of computer science. Did I tell you this story?
Well, that he invented.
All right, anyway, I told him I had written a book on mathematics for physicists, and he said to me, "Did you do the singular value decomposition?" And I said, "Yes." And he had thought that I would not have done it because most physicists don't do it and don't talk about it. In the education of most physicists, that thing was not done. And he realized, obviously he knew because he knows a lot of mathematics, he knew that that was the key theorem of linear algebra.
Can you repeat what you said? You take a positive definite matrix.
What's that?
Repeat what you said before. What it's doing is taking a positive definite
Well,
matrix.
A dagger A and AA dagger are automatically non-negative matrices.
Yeah.
So A dagger A and AA dagger are both non-negative matrices automatically. You can take, I mean, if you wanted, well, I don't have MATLAB running here, but you could just do what I did in that example. Example 1.46, I say x equals rand 33 plus I rand 33. Just take x prime star x in MATLAB, and you'll see you get something that is, well, you'll get something that's a 3 by 3 matrix, and it'll be real. But then you can do eig of that, and you'll see the eigenvalues are all non-negative. Okay, so let's see, there was one remaining, there was one loose end there, namely that let's suppose A is this sum UK, SK, BK. So what is AA dagger? Well, it's a sum UK, SK, BK, sum on L of now VL, SL, UL. And now this is just delta KL, and so this is the sum on K, UK, SK squared, UK. And so that tells you that the UKs are eigenvectors of AA dagger. That's the statement I made to you a little while earlier. Yes?
What was delta KL? Could you point again to it? Oh. Okay.
All right, let me give you a candy. Apparently I'm more accurate with my left hand than with my right hand. All right, so I think we've had enough about the singular value decomposition, unless there's one more question. Is there any more? Oh!
Sorry, I don't mean to belabor the point, but AA dagger, you just said that what's on the right, u sub k needs to be an eigenvector of AA dagger, right?
The
That's what you just
U's,
got done.
right, the U's are the eigenvectors of AA dagger. That is to say, AA dagger, UK, is SK squared, UK.
Okay.
And let me just for symmetry, the V's are the eigenvectors of A dagger A.
Yeah, okay, I'm sorry. It's been a long day, sorry.
No, it's all right.
I see it. I don't know.
Why don't you grab a candy from the...
It's good. The question wasn't worth a candy.
All right. Okay, so let me move on now to the Moore-Penrose pseudo inverse. Penrose, by the way, does general relativity, and
Is this Roger Penrose?
he's what?
Roger Penrose?
Yeah, I mean, I think it might be more than, might be his brother Sam. Okay, so we start out, now that we know about the singular value decomposition, no, let me just, since we've learned that the singular value decomposition is perfectly general, if you're doing anything in linear algebra, you could start with your matrix A, write it as a singular value decomposition, and then proceed, because you've now got it in the most useful form. And that's the starting point of the Moore-Penrose and inverse. So the pseudo-inverse, which unfortunately people write as a plus, I mean, it's -1 is the real inverse, so plus is kind of, you know, it's sort of a weird notation. In any event, the actual thing is this: sigma plus u dagger. So the V, so you just take this matrix V, you take the matrix U, but now what is sigma plus? Sigma plus is a little bit, is kind of amusing. Sigma plus is basically sigma transpose inverse in a certain sense, but I'm going to put quotes around this. So let me give an example. Suppose sigma looks like this: 1, 2, 3, and then say 0, 0, 0. Suppose sigma is a 3×4 matrix. Okay, let me tell you what sigma plus is.
Okay.
Sigma plus then is 1, 0, 0, but now with 2 you do a half. 3 you do a third. So you take the inverse and then you've just got zeros. So you take the inverse of the singular values and you take the transpose. Yeah.
Just confusion about which one's dagger and which one's plus.
Oh, hey, that's really something. All right.
The U is dagger.
That's another reason why the plus notation is really dumb.
Oh, okay.
So these are the, now this actually is a plus. But yeah, you're absolutely right. So this one, dagger.
Okay.
Okay, so what you do is you basically, you write V and U dagger, and then in the middle you do this funny thing where you take the transpose of the matrix, and in general it's rectangular, and then you invert numerically all the singular values, and they're all real and positive, so it's just 1 over. Now if they're 0, you just leave them as 0, you don't write the infinity. All right.
Oh, yeah.
Got the wrong glasses. All right. So, what are the properties of these? The properties are A plus, I'm going to write the plus this way. So that's like A inverse A would do this. And then A plus dagger and A pseudo inverse A dagger is so A plus behaves reasonably, and A plus A behaves reasonably under Hermitian conjugation. And A plus does the best it can as an inverse, but it's you know, it's by no means perfect. And I did an example on the computer there. I can give you another related example. We can set A equal to 0, 1, 0, 1, 0, 1. A plus, I'll just tell you what the answer is. It's 0, 1, 0, 1 half, 0, 1 half. And then you can verify that these two matrices satisfy these four properties. So these are the four defining properties of the pseudo-inverse, although the recipe is obviously a defining property. And the pseudo-inverse is also unique in that it's the only matrix that satisfies all these properties. Okay, and let's see. Let me just get. I printed out something from MATLAB this afternoon that might be worth looking at. Hold on. MATLAB had a slightly different set of rules here.
Sorry.
Oh wow. Are you okay? Actually, the MATLAB thing is the same as what I have, so. Yeah, I think the MATLAB is the same, it just looks different. Yes?
Why keep the first row unchanged of the original one? That's of the one that you're taking.
You mean this one here?
Yeah. Are you pointing to regular sigma or like the
That's
original
sigma and
matrix?
that's sigma plus.
Right. Why do you keep the first row the same? Is that something?
Oh, because the inverse of 1 is 1.
Right.
Whereas the inverse
Okay.
of 2 is 1
So
half.
that's not just a property of like you're just picking one for each of these.
Yeah,
just
if
so
I had,
happens.
you know, 4 here,
Okay.
this would be 1/4.
I was worried that you just kept the first row the
Yeah, I
same.
shouldn't have used 1. You want a candy?
That's okay. Thank you though.
So, is that not the general rule to construct the?
It is, yeah.
Why do we have?
It's a general rule for sigma plus.
Why do we have 1/2 on A plus?
Oh, because there are two different things. You go from sigma to sigma plus this way, all right? Whereas you go from A to A plus this way,
Oh, okay.
all right? And you see, because with sigma you've got something that's only has a diagonal,
Okay.
apart from the degree at the end. And we're, okay, so I mean, literally what happens here is that this A plus, I mean, if you look at the example, it's really written as V sigma plus U dagger. Okay, now, there's this term, the rank of a matrix, and if you just say rank, parentheses, name of the matrix, close parentheses, MATLAB will tell you what the rank is. There are four independent definitions, all equivalent. So the rank of A is 1, number linearly independent rows. 2, number linearly independent columns. 3, number non-zero singular values. And 4, number, rows, or dimension of our, or maybe I should have just said dimension, that would make more sense. Dimension, biggest, square, non-singular submatrix. Okay, so I'm abbreviating because it's written in the book and I'm just repeating it, but the idea is if you have a matrix and it has so many linearly independent rows and so many linearly independent columns, that's the rank. And then the number of non-zero singular values and the dimension of the biggest non-zero submatrix. So an example that I gave here was 1, 2, 4, 0, 2, 3, 101, minus 2, 2, 1. And it has 3 rows, so the rank can be at most 3. On the other hand, twice the first row, 2 row 1 plus 3 row 2 minus 2 row 3 is 0. So the rows are not linearly independent, they're linearly dependent. So that means the rank can be at most 2. And in fact, it is 2. Now I mentioned software here, I forgot to mention Python. Python is free software that's available, and some people like it a great deal. Okay, the tensor product. This is something that occurs oh God, we're out of time.
Did you still want us to do the two?
All right, well, let me just say this then. I'm a little concerned about having assigned problems from chapter 2 when I haven't started lecturing it. Is that okay? Do you think so? All right, I'll go with that. Thank you.